Hello everyone, this is Doug, and in this video we're going to continue our discussion of osmosis and diffusion and focus on osmosis. And we'll try to point out how it's different than diffusion. If you remember from the first part of this little pair of videos, right, diffusion was defined as just the movement of any particle down its concentration gradient, right, from high concentration to low concentration. And remember that it could be any particle. It could be a gas, it could be a liquid, it could be an ion, it could be a molecule, it can be just kind of anything, and there just needs to be a concentration gradient, and it will move down that. Now, osmosis is a lot more specific. Osmosis, you need a little bit more going on, right? Osmosis is the movement of water specifically. Not any particle, water. Good old H2O, that's it. That's all we're talking about with osmosis when we talk about osmosis in chemistry and biology. It's the movement of water. So no ions, nothing like that. And the other really crucial, important thing about osmosis is that it requires what's called a semi-permeable membrane. And when we're talking about semi-permeable membranes, what we're saying here is we need something that is only permeable to certain things, namely just water. So semi-permeable membrane means that it's only permeable to water. Only permeable to water. That's it. Or in other words, no solutes can cross. And with diffusion, right, we did not have that same limitation. Diffusion, like I don't know if you remember from that first video, I did the one with the stink bomb, right? There was no membrane at all there, right? That was just a smell moving across a room. You don't need a membrane for diffusion, but you do need a semi-permeable one for osmosis. And what we're going to see in osmosis is that water is going to move from low concentration to high concentration. That's what we're looking at. And so I'll start off with just kind of a generic example, and then we'll move into some more biological ones here. I have what's called a U-tube here. It's a U-shaped tube. It is not like the website you're watching right now. It's called a U-tube because it's shaped in a U. And what we have here, right, is this thing in the middle. This is supposed to be your semi-permeable membrane. So here's that little blue dot thing. This is your semi-permeable membrane. And so the idea here is that initially what you do is you separate these two solutions. You have these two solutions and they're separated by this semi-permeable membrane. And then you ask yourself what's going to happen to these solutes and to this solvent, to water. And I wrote down here, right, that on one half we have sodium chloride at a 0.1 molar solution. So we've got that on the left-hand side here. So we've got one side that's 0.1. We've got one side that is 0.2 molar, right? So they're different concentrations. We need to have a concentration gradient, or we need to have a different concentrations in order for osmosis to occur. And then we ask ourselves, well, what's going to happen here, right? On the right-hand side, it looks like I have more sodium and chloride ions. I tried to just draw a few here. And on the left-hand side, I have fewer sodium chloride ions. Now, if we were talking about diffusion, we would be saying that, oh, well, there's more chlorides on the right, so maybe they want to move left. And that would be true for diffusion. The sodium ions and the chloride ions do want to move left. The problem here, right, is that they cannot move left, right, because it's a semi-permeable membrane and solutes cannot cross. So yes, chloride might want to move left, but it's going to bounce off of this membrane and it cannot pass it. Same thing with sodium. It's going to try to get through the membrane, but it cannot because this membrane is semi-permeable. It's not going to allow the solutes to pass. So solutes cannot pass, but still we want for these concentrations to end up being equal, right? That's what happened in diffusion, and that's kind of what's going to happen with osmosis, which I think is why people confuse them so much. So if the solutes can't pass, but water can, it must be that water is the thing that's going to move. And so if I want these two solutions to become equal, right, I have a less concentrated side and a more concentrated side. I need to dilute the more concentrated side. In other words, I need for water to move from left to right. I need my water to go from the less concentrated side onto the more concentrated side, right? Because as water leaves the left-hand side, that's going to make its concentration go up. And as water moves to the right-hand side, that's going to make its concentration go down. And so ideally what you're going to see here, right, is after a period of time, it kind of depends on what your membrane's like and how much volume you have, you're going to see the water level of the left-hand side go down and the water level of the right-hand side go up, because water is literally moving across. It has moved across that membrane is the idea. So it has moved for sure. And what should happen at the end in most cases, right, is what you're going for is for an equal concentration on both sides, so that now the concentration of sodium chloride ions is approximately the same. In my case, right, it would be assuming these were equal volumes to start off with, 0.15 molar, right? So somewhere exactly between 0.1 and 0.2, right? So what we're going for, the goal is to have equal concentrations. And I'll write that right here. All right, so the goal of osmosis is to have equal concentrations of things. I'm going to try this up here. So the goal is to have equal concentrations at the end. Then osmosis stops, just like diffusion would stop. And then we'd have no more osmosis. And again, the water levels would literally change. And this is a really important phenomenon. Osmosis is in a lot of biological aspects. It's how roots get water out of the ground. It's how trees get water. It's partly how trees get water all the way up to the tops of some giant tree. You see osmosis occur all the time. So let me give you an example with fish. I don't know if anyone has aquariums or is vaguely aware of this, right? But you can't put a saltwater fish in a freshwater tank, and you can't put a freshwater fish in a saltwater tank, at least not most species. And that's largely because of this problem of osmosis, right? If you're looking at a freshwater fish here, the idea is that if it's used to living in fresh water, it's used to a relatively low concentration of solutes, right? It's freshwater, it's not saltwater. So low concentration of solutes. So in our little fishy here, we have a low concentration of stuff. Now, if you look at your saltwater, right, saltwater by definition is going to have a lot of salts in it, right? So it's called saltwater. So this is going to have a much higher concentration. A much higher concentration of solutes. So here we have high concentration. And again, right, so cell membranes and stuff like that, right, the fish isn't going to let in and out a whole bunch of salts, and even if it does, it's going to be much slower than the movement of water. So we want to ask ourselves, well, what happens to the water molecules either inside or outside this fish, right? It's surrounded by water. If you put it in a saltwater tank, or in this case, a saltwater tank, fish has got water inside of it, and it's surrounded by water, right? You put it in this tank. So the question is, what is going to happen then with those water molecules? Are water molecules going to move into the fish or out of the fish? Well, according to osmosis, right, we said that water always moves towards the area of higher concentration because it's trying to dilute that. It's trying to make the concentrations on either side of a membrane equal. And so since there is more water, right, there's a higher concentration of solutes on the outside of the fish, what we see is that water is going to leave this fish. Water is going to leave this fish, and it's going to dehydrate the fish. So it's going to dehydrate the fish, which obviously the fish is not going to be happy about. It's going to, at the very least, get injured for a little while. At worst, probably die. You have to be really careful about the salinity and stuff if you have like a saltwater tank and you're trying to put whatever fish in there. Now, there are some fish, like salmon, for example, who can go back and forth between saltwater and freshwater, but that's not the norm. Most fish need to have a certain salinity that they've grown accustomed to, so this osmosis is not taking place and not killing them. This is also, I mean, I'm not trying to like endorse this or anything, but this is also what happens if you've ever heard of anyone trying to put like salt on a slug or a snail, right? You just make it super salty outside of that slug or snail, and then all the water leaves them and they don't do so hot. So osmosis definitely occurs in biological systems. So let's talk about cells also here. So really, osmosis is very important for cells because of something called aquaporins. If you take a look at a cell, right, cells actually are semi-permeable membranes. The cell membrane is a semi-permeable membrane. So I'll write that here. The cell membrane is a semi-permeable membrane. And I mentioned this in the last video, semi-permeable membrane. Right, which means that basically only water can pass through it. So only water can freely pass. And that's because of these suckers. I drew little things on my cell here. This is supposed to be a particular membrane protein called an aquaporin. Aquaporin. And the idea is that there's a whole bunch of these aquaporins located all over the cell. And it turns out they're really, really important for some cells, how they move, how they change shapes. But mostly they just let water kind of freely move in and out. And again, because the cell membrane is a semi-permeable membrane, it does not allow solutes to freely move in and out. Again, this is most solutes, not some small nonpolar things. But generally speaking, right, things like glucose and chloride can't just freely move across the cell membrane. So, like I said, this allows water molecules to freely go really wherever they want, right? So a water molecule can move out of this aquaporin, a water molecule can move into this aquaporin. And the normal concentrations in like a red blood cell, for example, the concentration of solutes here is going to be about 0.28 molar. That's the total molarity or the osmolarity of all of the different solutes, all the things that are dissolved in the intracellular fluid. And ideally, right, outside of the cell in the extracellular fluid, it's the same concentration. It's also 0.28 molar. And so if you have the same concentration of stuff inside the cell as you do outside the cell, what happens is that you see no net movement of water, right? No net movement here. No net movement of water, right? Because there's the same concentration inside and outside, so osmosis is not occurring. Water's just moving in and out of the cell however it wants. Now that's going to change if that extracellular fluid is no longer 0.28. And so we need to take a moment to talk about tonicity, because that's going to kind of dictate what happens in terms of osmosis. Like for this, sorry, we'll get to tonicity in one sec. So I was just going to say, for example, if it was not the same, right, if it was not the same concentration, so here I have 0.28 and 0.30, and I have, again, if I have water on the inside and I have the water on the outside of the cell, now in this case, my 0.28 is less than my 0.30, and so water is going to leave this cell to try to make it so those concentrations are equal. So we're going to see water leave the cell. And now we're going to talk about tonicity, because now we have different total molarities, and so water is going to want to move, which is what tonicity is all about. So tonicity. It's describing the movement of water in and out of a cell based on the total molarity outside of the cell, right? The inside of the cell is roughly 0.28 molar. That's the total molarity, the osmolarity of inside of a cell. But what's occurring outside of the cell could change for a variety of reasons, either like IV bags or some diseases, or maybe you're not filtering out certain particles and you're getting a lot of fluid buildup. And so we have solutions that are called either hypertonic, isotonic, or hypotonic, right? So hyper, iso, hypo. Where if I look at these words, right, the word hyper, you've probably heard of somebody being hyper. Hyper means like too much or too high. So too much, too high. So if someone's hyperactive, that just means they're like too active, they've got too much energy. Iso, we've seen this prefix a lot. Iso means the same. Remember, things like isomer have the same pieces. Isotopes are really the same. They're the same element. They just have different numbers of neutrons. So iso, I just wrote iso. Iso means the same. And then hypo means too low, right? So you might think like hypothermia means like your temperature is too low, or hypodermic needle means it's below the skin, a little below the dermis. So hypo means below. Hypo means below. And so what they're talking about is they're talking about the concentration outside of the cell. Is the concentration outside of the cell too high? That would be hypertonic. Is the concentration the same as the cell? That would be isotonic. Is the concentration below what it should be in the cell? That would be hypotonic. So let's take a look at some of these here, right? So let's say, for example, in the hypertonic, I'll just give you a molarity. Let's say that the solution around this cell, the molarity is higher, right? It's too high. It's hypertonic. Higher than 0.28. Let's say it's 0.34 molar, right? So that's saying that the concentration outside of the cell, the extracellular solution, has more solutes. If there are more solutes outside the cell, right, remember that water chases the solutes. Water is going to go to where the more solutes are. So what you see is that water leaves the cell, and the cell shrivels up or undergoes what's called crenation. So I'll say that the cell shrivels, and that's called crenation. crenation is when the cells kind of get wrinkly, and it can affect their functions if they get too their shape changes too much. If it's isotonic, right, that means it's the same, right? Iso meaning the same. That means it's the same concentration. That means that the molarity outside the cell is the same as what's inside the cell, which is that 0.28 molar. And so that means that nothing occurs, right? There's no net movement of water. No net movement of water. So no net movement of water. Because there's no driving force there. The concentrations outside and inside are the same, so we're good. Now, if I look at our last example where it's hypotonic, where it's below the concentration, so I'll say that the molarity here is 0.22 molar. Right now, the idea is that if it's too low, now the idea is that the cell at 0.28 is higher than the outside of the cell, which is 0.22. So now water wants to move into the cell. And so what you see is that the cell will swell up or potentially explode. So the cell will swell, potentially bursts. All right, depending on how big the difference is. Here's a little picture of a cell bursting. And so it's really important. So tonicity describes the movement of water. Will water move out of the cell? Or in other words, is the solution hypertonic? Will there be no net movement, in which case it's isotonic? Or will you see water move into the cell, which means it's hypotonic? Now, I have to kind of mention, I'm going to post a link to this video, but there is a difference. I put some concentrations here. What I was assuming with all these concentrations is that none of these solutes in the extracellular solution were able to be transported in or out of the cell. Because osmolarity is not the same thing as tonicity. Tonicity just describes the movement of water. Osmolarity is the actual concentrations of stuff. And there is a difference between those two things. So what all of my examples are assuming, and I'll write this in red here. I don't know where to write this. I'll write it over here. All of this is assuming... Sorry, I don't know what happened there. All of this is assuming that none of the particles, that none of these solutes, none of the solutes outside the cell outside the cell could be transported in. I'll say transported. So we're assuming that whatever was in these solutions here that I drew in purple, right? So like this right here and right here, that though whatever was making up that 0.28 or that 0.34, those could not have been moved in. So for example, glucose. Because like if there were glucose would just be sucked in and that concentration would drop. So we're just assuming, right, if I give some concentration that none of those things could move in, so we can talk about this tonicity effect. Again, I'll post a link from someone doing a really good job describing the difference between tonicity and osmolarity. And it kind of depends on what the solutes are. That's beyond what I need you guys to know in this class. I'm not trying to teach cell bio or A&P. I just want you to know that osmosis occurs. It occurs in cells. Water is going to move towards the more concentrated side. That's what I'm looking at. So if I went back to this example here, right, where I had my extracellular fluid and it had a concentration of 0.30, right, again, we would say that, okay, well, water is going to move out of the cell membrane. Water is going to move out of this because that's a higher concentration. And again, we're assuming that none of the things that make up this 0.30 can move in, so it's just going to stay 0.3. And so we would say that this solution here, I would say that this solution is hypertonic. This would be a hypertonic solution. And how do I know it's hypertonic? So hypertonic solution. I know that it's hypertonic because water leaves the cell. Right, if I see water leave the cell, that means it was a hypertonic solution. And that should mean that there are more solutes on the outside. is the idea. Since this is 0.30 and that's higher than 0.28, they should coincide, but again, we're always going to assume that those solutes in the extracellular fluid cannot be transported in. So that's kind of what I want you to know about osmosis, right? It's a little more specific than diffusion. Osmosis is the movement of water across a semi-permeable membrane, whereas diffusion is the movement of any particle down its concentration gradient. So osmosis, you need that semi-permeable membrane. You see it a lot in biological systems. Those are the big ideas. So hopefully you feel a little bit more comfortable on what osmosis is and how to predict where water is going to move. And if you have any questions or comments, please leave them down below. Have a great day.